Waves. They're literally everywhere. They're in the light that's letting you see this right now. They're in the sound of my voice reaching your ears, and they're what makes the phone in your pocket work. But what is a wave really? Okay, let's dive in and figure this out.
Of course you have. I mean, we've all been there, right? Just sitting on the sand, watching that endless, hypnotic rhythm of the ocean. It's one of the most powerful and, honestly, most calming things on the planet. And it's our first best example of a wave.
I mean, it sure looks like all that water is making a long trip from way out at sea just to crash on the beach. But is that what's actually happening? The answer is probably not what you think. And it's the absolute key to understanding pretty much every wave in the universe.
So let's stick with the ocean for just a minute. What kicks all this off? What gets these massive bodies of water moving in the first place? Well, it turns out the culprits are both right here in our atmosphere and way, way out in space.
The first one is pretty obvious: wind. When wind blows over the water, that friction grabs the surface and creates a little disturbance. And if the wind keeps blowing, that little ripple can grow into a monster wave. But there's a much bigger, more powerful force at play too: gravity. The pull from the moon, and to a lesser extent the sun, literally tugs on the Earth's oceans, creating these enormous, planet-wide waves that we call the tides.
I know, that sounds super technical. A propagating dynamic disturbance, but let's break it down. All it really means is that a wave isn't a thing. It's a change that travels. It's a disturbance moving away from the normal, calm state. You know, like when you drop a rock into a perfectly still pond and the ripples spread out. That ripple is the disturbance, and that idea is going to be crucial.
Okay, so if a wave is a disturbance, let's get under the hood and look at its anatomy. These are the basic properties that define all waves, whether we're talking about the ocean, or sound, or even light itself.
And this right here, this is the answer to our big question from the beginning. That bit of water out in the ocean, it doesn't actually travel all the way to the shore. If you put a rubber ducky out there, it would mostly just bob up and down in the same spot. That's because it's the energy from the wind that's traveling across the ocean. The water itself is just the medium that the energy is passing through. So remember this: waves move energy, not stuff.
So this energy disturbance travels in basically two main flavors. The first is a transverse wave. This is where the particles move up and down, perpendicular to the direction the wave energy is moving. Just picture flicking a rope. The wave zips forward, but the rope itself just moves up and down. The other kind is a longitudinal wave. Here, the particles move back and forth in the same direction as the wave. This is more like giving a slinky a push from one end.
Now, to describe any wave, we need to know its specs. First up is wavelength. We use the Greek letter lambda to represent it, which is kind of cool. All it is the physical distance from the peak of one wave to the peak of the very next one. It's literally the length of a single wave. Next up, we have frequency. So if wavelength is how long a wave is, frequency is how often it shows up. If you just stood still and counted how many wave crests passed you every second, that number, that's the frequency. And we measure it in a unit called hertz, where 1 hertz is just 1 wave cycle per second.
And the final key ingredient is amplitude. This one's simple. It's the wave's height. It's how intense the disturbance is. And this is the spec that's tied directly to a wave's energy. A wave with a massive amplitude is carrying a ton of power. One with a tiny amplitude, not so much. It's the difference between a devastating tsunami and a tiny ripple in your teacup.
Okay, so now we have our basic toolkit: wavelength, frequency, and amplitude. Let's apply it to something we experience every single moment of our lives: sound. Sound is the perfect example of a longitudinal wave.
Remember that slinky analogy? When you give one end a shove, you create a little bunch-up of coils that travels down its length. Well, sound works exactly like that. A vibrating object, like a guitar string or your own vocal cords, pushes on the air molecules around it. It squishes them together into a high-pressure zone called a compression. Then, as it moves back, it leaves a low-pressure gap called a rarefaction. That traveling chain of squishes and stretches is the sound wave.
And here's where all that physics connects directly to what we experience. A sound wave's frequency,
Our brain interprets that as pitch. A high-frequency wave gives us a high squeaky sound. A low-frequency wave gives us a deep, low rumble. And the amplitude? That's what we perceive as loudness. The higher the amplitude, the more intense the vibration, the louder the sound. It's that simple.
Now, because sound is a physical wave, it has to have a medium, a substance to travel through. And that substance matters a lot. Just look at the difference here. Sound moves fastest in solids, like steel, because all the atoms are packed so tightly together, they can pass that vibration along almost instantly. It's way slower in a gas like air, where the molecules are all spread out and lazy.
So, we've talked about ocean waves and sound waves. They're both mechanical, meaning they need stuff to travel through. But there's a whole other, much stranger class of wave out there. And these waves make up most of the reality we know.
Meet electromagnetic waves, or EM waves. This family is huge. It includes visible light, radio waves, microwaves, X-rays, the whole shebang. And they have one totally bizarre property that sets them apart. Unlike sound, they don't need a medium. They are their own self-propelling disturbance in electric and magnetic fields. This is how light from a star billions of miles away can cross the absolute total emptiness of space to reach us.
Let's just focus on one slice of that giant EM spectrum, radio waves. It's really amazing how we've organized this. By using different frequencies, we can send all kinds of information at the same time without it all turning into a jumbled mess. Down in the lower frequencies, like medium frequency or MF, you get AM radio. Move up the dial into the very high frequency range, VHF, and that's where you find FM radio and TV signals. Go even higher to ultra-high frequency, or UHF, and now you're in the realm of mobile phones and GPS. It's all just waves.
All right, for our last section, we're going to bring this all home. We're going to take our understanding of sound waves and combine it with some amazing technology to see how waves are used to save lives every single day.
It sounds like something out of science fiction, doesn't it? But it's a totally routine medical procedure. The key is to use sound waves that have a frequency so high it's way beyond what any human can possibly hear. We call it ultrasound. The whole process is really just ingenious. First, a little handheld device called a transducer sends quick pulses of this high-frequency sound into the body. Second, those waves travel through the soft tissues, but when they hit a boundary, say between your liver and your kidney, or between fluid and a solid mass, some of those waves reflect back, creating an echo. Third, the very same transducer that sent the pulse listens for those returning echoes. And finally, a computer cleverly analyzes how long it took for the echoes to come back and how strong they were, and uses that data to build a live, moving picture of what's going on inside. And the things we can see with this are just incredible. It's most famously used to check on a baby's development during pregnancy. But doctors also use it to find tumors, to spot painful kidney stones or gallstones, and even to watch the heart beating in real time. That's called an echocardiogram. It's a completely safe, non-invasive window into the body, all thanks to the simple physics of sound waves.
So when you really stop and think about it, waves carry everything. From the quiet energy of a whisper, to the ancient light of a faraway star, to a life-saving image of a human heart. They are the universe's fundamental delivery system for energy and for information. And that just leaves one big question. What will they help us discover next? Thanks for joining this explainer.